Welcome to a lesson with Dr. Powell. Let's take another look at the second derivative test, particularly for a function that has two inputs and where we're trying to find a maximum or determine if something's a maximum or a minimum. The second derivative is a 2 by 2 matrix. Now, these matrices are what we call symmetric, meaning, for instance, that fxy is equal to fyx. So across the diagonal from here to here, they'll always be the same. This is true for nice, smooth functions, and those are the ones we work with here in this case. So, for instance, we might have something like 2, 3, and maybe we have like a -1 and a -1. Because across, it's the same. Now, the diagonal doesn't matter what it is, but across the diagonal this way, these guys must be the same. So now let's just kind of consider what that means. When we take a determinant after we make everything here negative, and then we put on an x here and an x here in the diagonal, and we're taking the determinant, look at what's happening. We have something like x minus 2 times x minus 3. And then this number, when we subtract, since these guys are the exact same, you're always going to get a negative. So, for instance, if we had started off in our original matrix, if in our original matrix both of these were positives, then when we make everything negative, that would even be negative. But notice, -1 times -1 and then another negative still becomes negative. So this guy's always negative. Well, what does that mean? Well, consider just graphing this as a function if you had y equals. This is a parabola with two intersects at 2 and 3 even. I mean, it's going to intersect and it's going upwards since it's, an x squared. Now, notice what happens when we shift this down. It just lowers this. But look, do you see how it still has x-intercepts that are real and not complex? In fact, this is true for any symmetric matrix. When we go through this, we're always going to get real zeros or real roots of this quadratic that we have if we set this equal to 0. So that's the first thing to notice. So we're for sure going to have everything real. Now, in order to we don't actually have to find out what those intercepts are. We just have to know if they're both positive or both negative or one of each. If it's one of each, it's a saddle point. And that's if you have a positive and a negative. If they're both positive, then you know it's a minimum. If they're both negative, then you know it's a maximum. So we just have to know this. We don't really have to know anything more. So it'd be nice if we can kind of come up for some rules for how to determine this. For instance, let's look at this particular case right here. If we multiply this out, we end up getting x squared minus 5x plus 6 minus 1. In other words, just plus 5. So looking at this, we can use something called Descartes Rule of Signs to help us investigate this a little bit and maybe some other thoughts, especially since we know that both of the roots are real and none are complex. So let's do that. So let's do x squared minus 5x plus 5. Okay, now for starters, notice how if we just look at the polynomial the way it is, we see two sign changes. That automatically, if you see two sign changes, that automatically tells you that there are either 2 or 0 positive roots if you set this equal to 0. That's Descartes' Rule of Signs. So the number of sign changes is the maximum number of positive zeros, and then you always have to go down by an even number. Here, there's 2 at max, and anyways, you have to go to 0. So you know it's either 2 or 0. But also, if you were to plug in a negative x everywhere, let's try that and do the same trick. It's like you're reflecting the negative part over to check for positives again. Let's do that. When we do this, we get x squared plus 5x plus 5. Notice that when we reflect over and count, there's none. That means there's 0 negatives. Since we know that there are precisely 2 reals, and they have to be positive or negative, that means there's 2 positives and we're done. So that means that if we were dealing with this polynomial at this point, we would be looking at a minimum automatically just by looking at the sign changes. See the sign changes? We're good there. Now, let's look at some other cases and see kind of what we can get from that. For instance, let's take a look at another example. What if we had a second derivative that looked something like this? Maybe we had a, let's see, suppose we had something like a minus 4 and maybe a -1. And then maybe we had a, let's just do a 1 and 1. Okay, so we're looking at something like this. And so we do the same trick, and here we have, let's see, x plus, and these are minus. Okay, but then we get an x plus 4, x plus 1, and then we have what, a -1 going on, right? Or yeah, -1. Okay, multiply this out. We have x squared plus 4x and x, 5x, plus 4 minus 1, so plus 3. Notice that this is the polynomial we get. There are no sign changes at all. So that means that there are 0 positives. Since we know that there have to be 2, that means there's 2 negatives, and we're done. We know it's a maximum without ever solving for the roots. We know precisely there are 2 negative roots, and so this would guarantee that we have a maximum via this little rule, Descartes' Rule of Signs. So just counting sign changes can help us with that. Okay, now what about a saddle point? So we've talked about giving an example for a minimum and a maximum. Now let's look at an example for a saddle point. Okay, so for this, let's imagine that we get a matrix for the second derivative that looks something like this. Perhaps we have, let's see, -2 and 1, and maybe we have 3 and 3. Okay, let's take a look at this and see what we would get. So we'd have x plus, x minus, and minus, take a determinant, we get x plus 2, x minus 1, and then we have a -9. Okay, so looking at this, we get a x squared plus 2x minus x, so plus x, and then -2 minus 9, so we get -11. Now, using the same technique of sign changes, notice we go plus, plus, minus, there's only 1 sign change. That means there's exactly 1 positive. Since you know there's 2, guess what that tells you? 2 total. That tells you that there are, so 2 total reals, so either positive or negative. That means there has to be 1 negative, and we're done. We know there's 1 positive, 1 negative, and we know it's a saddle point. Saddle point. Just automatically, just looking at it. Now, if our polynomial read something like this, x squared minus x minus 11, then actually we would know also a saddle point for the same reason, because there's 1 sign change, plus, minus, minus. So, and you can, in particular, note that, so that's kind of the way that we could tell this. Just by using Descartes' Rule of Signs, we see the saddle point if we just notice 1 sign change, and we have it. Thanks for watching.